Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. So in today's class, we are going to discuss about the coupling coefficient. Of course, in the previous classes, we have already covered some topics from these magnetic circuits, which are what is the Faraday's law of electromagnetic induction and the concept of self and mutual induction, and as well as the dot convention also we have discussed, and some numerical problems based on these topics also we have covered in the previous classes. So of course in the previous class we have discussed some basics about these coupling coefficient. So in today's class we are going to discuss in detail about the coupling coefficient, okay, and then we will also discuss some numerical problems based on this coupling coefficient, because in the previous class we just written what is the equation for this coefficient coupling, that's all, but we didn't discuss much about this coefficient coupling. So in today's class we are going to discuss about this coupling coefficient, or sometimes coefficient of coupling also they usually call. So here the coupling coefficient or the coefficient of coupling, which is represented by the small k, which is the degree of fraction of magnetic coupling that occurs between the circuits. Because of course when there will be the magnetic coupling or the coefficient of coupling, if there are two circuits when are placed each other, then we know already there will be a mutual induction between these two circuits, okay. So which means the current flowing through the one circuit, okay, because here let us consider two are windings, okay, two windings are there. So let us consider here are the circuit 1, this is circuit 2. So when the current flowing or change in current flowing through the circuit 1 will cause the voltage appear across the secondary terminals, secondary circuit terminals, okay, because due to the mutual induction principle, right? So which means here the amount of the voltage which is produced in the produced across the secondary terminals, okay, is depends on the degree, okay, so the degree of the magnetic coupling between the two circuits, right? So which means it is based on the coefficient of coupling. So which means here it can also defined as the ratio of flux linking the two circuits by the total flux produced. Which means suppose here the total flux produced, here it is, let us consider the total flux means, let us consider here we have applied some voltage across the circuit 1, so that the current will flow through the circuit. So due to the change in current, of course the magnetic field will produce, and the same field is linking with the circuit 1 itself, which is called the self inductance, okay, or the self induction, and some amount of the flux, okay, is also linking with the secondary winding, so which is called as a mutual induction, because of the mutual induction, so that the current will flow through the secondary circuit, so that there will be some EMF will produce or CMF will produce across the secondary terminals, right? So which means here, or in another words, let us consider here the phi or phi 1. So phi 1 is the flux produced by the flux produced due to the change in current flowing through the winding or the circuit 1, and the flux linking with the secondary winding, let us consider here it is phi 1 2. Okay, so here the phi 1 2 is the flux linking between the two windings, right? So which is the mutual induction, due to the mutual induction. So then the equation will become here the K is equal to here phi 1 2, the flux linking between the two circuits is phi 1 2 by the total flux produced, here it is phi 1. Which means here whatever the flux produced by the primary winding may or may not be linked with the secondary winding, okay. So if whatever the flux produced by the primary winding is okay linked with the secondary winding also, then here the phi 1 will become phi 1 2, right? Because the same amount of the flux is linking with the secondary winding also, right? So that here if you substitute the phi 1 2 as a phi 1, then phi 1 by phi 1, so which is equal to 1. This is one case. And another case, suppose if there is no flux linking with the secondary winding. So which means here the phi 1 2 which is equal to 0 because there is no flux linking with the secondary winding. Then here if you substitute phi 1 2 as a 0, then 0 by phi 1 which is equal to 0. Which means the minimum value for this coefficient of coupling is 0 and the maximum value for the coefficient of coupling is 1. So which means here the coefficient of coupling will always in between the 0 and 1. So it should be greater than or equal to 0 and less than or equal to 1. Right. So then based on this value, which means the k is ranging from 0 to 1. So based on this value, okay, so here the strength of the magnetic field which is linking with the secondary winding can be measured. So this is the coefficient of coupling, right? And in the last means in the previous classes we have seen the equation for the coefficient of coupling, okay, are in terms of mutual inductance actually. So let me write for the first the coefficient of coupling k is equal to here the mutual inductance m by square root of L1 into L2. So this is the equation that we have discussed in the previous class. Then how we get this equation? So in today's class we are going to derive, okay, so this equation. So how we can derive from this concept of the coupling circuits, right? So for that here, of course, again I am just considering the same circuit which we are discussed just now, right? So here first as we know, let me write the equation for the inductance, right? Because as we know here inductance for the first circuit is there, inductance for the second circuit is there. So instead of writing the primary inductance or the secondary inductance or the inductance of the circuit 1, inductance of the circuit 2, okay, or the self inductance, in another words we can also call it as a self inductance. So generally I am writing L is equal to N into phi by I. We know already what is N. N means the number of turns and phi is the flux linkage and I is the current flowing through the particular circuit, right? So which means suppose if it is L1, okay, so with respect to the circuit 1, then here L1 is equal to, then let us consider here the number of turns for the primary winding is N1 and here the flux produced by this winding is phi 1 and the current flowing through this particular winding is I1, let us consider, right? So similarly L2 is also, which is N2 phi 2 by I2, right? So let us consider from this, okay, we can also find the phi or the phi 1. So let me find here the phi 1. Phi 1 is equal to, you just send this one. So here L1 I1 by N1. Let us consider this is equation number 1, right? Then we know already the mutual induction, the mutual inductance equation, because we have already discussed in the previous classes what the concept of self and mutual inductance. So we know the equation for the mutual inductance, which is M is equal to N2 phi 2 by I1. N2 phi 2 by I1. Or in another words, I mean this is with respect to the secondary winding. Okay, with respect to the primary winding, we can write one more equation. Let me write here. So which is M is equal to, we can write here it is N1 phi 1 by I2, right? So both can be possible, right? Or in another words, we usually write it as this is M21 and this is M12. Okay, but we know already M21 is equal to M12, which is equal to M. So that's why instead of that, we simply we are taking it as a M. Okay, so then here just let me take only M. M is equal to N2 phi 2 by I1, right? But the flux linking with the secondary winding, okay, so the flux linking with the secondary winding, okay, are we usually considering, before we considered as a phi 2 1, but instead of that here let us consider this is phi 1 and this is the phi 2, okay. Then the flux linking with the secondary winding, which is phi 2 is equal to k into phi 1, okay. Then substitute this phi 2 value in this equation, then here this equation will become M is equal to which is N2 into K into phi 1 by I1, right? So here we, from equation number 1 we know the value of phi 1, then substitute the phi 1. Let us consider this is equation number 2, Okay, so just substitute equation 1 in 2, equation 1 in 2. Then here this will become n2 k by I1 into here L1 I1 by N1, which is m is equal to. Okay, so this we can simplify because I1 gets cancelled. Then here this will become k into N2 by N1 into L1, right, which is equal to m. Okay, then from this equation we can make it as here it is N2 by N1, N2 by N1. Just send the other terms which is k and L1 to what is that, the left hand side. So then it will become m by k into L1. So let us consider this is equation number 3, right? Yeah, equation number 3. Then now let us just make it, what is that, the circuits are reversed, which means this is how we have calculated the mutual inductance M, which is because of the current flowing through the primary winding. So let us find the same mutual inductance, because like this. Now let us find the same equation, now this one. So substitute the same phi 1 in this equation. Okay, then here you will get M is equal to here k into N1 L2 by N2, right? Then the same way, just try to find here, this is N2 by N1 is equal to M by 5, right? Then yeah, the same way here, let us find here N2 by N1. So from this equation, then here N2 by N1, which is equal to N2 by N1, which is equal to here k into L2 by M. So let us consider this is equation number 4. Okay, so from equation number 3 and 4, okay, so what we can write, because here this N2 by N1, the equation number 3 is representing N2 by N1 and equation number 4 is also representing N2 by N1. So then which means here N2 by N1, which is equal to, so from the first equation here it is M by K into L1, and from the fourth equation here it is K L2 by M, K L2 by M, right? So then here, if you just what is that, cross multiply this, then here which is M square, which is equal to here K square into L1 L2, right? So which means here M is equal to K into square root of L1 L2. So this is also one of the equations. So the mutual inductance in terms of the coefficient of coupling or the coupling coefficient. And from this equation also we can find the coefficient of coupling. So K is equal to M by square root of L1 and L2. So this is how the same, the equation which we used in the previous class is derived like this, right? So now here, this is very important, the equation, because we are going to solve some problems based on this equation. What is the coefficient of coupling, or how to calculate the coefficient of coupling when we know the mutual inductance as well as the self inductances of the individual coils, right? So this is the concept of coefficient of coupling, right? So first thing is, we should get to understand what is the coefficient of coupling and how important it is. Okay, so when we are going to apply the mutual induction principle, right? So then now we are going to solve some problems, numerical problems, right? So first let me read one simple problem. Okay, so the two coils have the self inductance of 250 millihenries and 400 millihenries respectively. Then determine the magnetic coefficient the magnetic coupling coefficient of the pair of the coils if their mutual inductance is 80 millihenries. Of course, this is the direct question. I mean, if you remember the equation, we need to just substitute the parameters in that particular equation. Then we can simplify. Then you will get the answer, right? So here, first let me write the given data. So what is the given data? Here the two coils having the self inductances. So which means the two coils L1 and L2 we usually consider. So here L1 is equal to 250 millihenries. Then similarly L2 is equal to 400 millihenries. And another parameter that they have given is mutual inductance. So mutual inductance M is equal to 80 millihenries. Then what we have to find? We have to find determine the magnetic coupling coefficient. Okay, which means the K. So as we know here, K is equal to M by square root of L1 L2. So just substitute the values. Okay, so here 80 into 10 to the power of minus 3 henries by square root of here 250 into 10 to the power of minus 3 into 400 into 10 to the power of minus 3. Right. So if you simplify this, then you will get the answer for the magnetic coupling coefficient, which is K is equal to 0.253. Of course, this is a constant value, so this particular value doesn't have any units, right? So K is equal to 0.253. Very simple. Okay, so just we need to remember the equation for the what is the magnetic coupling coefficient or coefficient of coupling, whatever it may be. Okay, so some textbooks they usually calling as a coupling coefficient, and some textbooks they call it as a coefficient of coupling. Okay, of course, anyway, in all the cases that is for the magnetic circuits only, right? So this is how we can solve the problem. Then coming to the second, of course, the second one is also simple, not very difficult. So let me read the problem here first. The two coils X and Y having the self inductance of 80 millihenries and 60 millihenries respectively are magnetically coupled, and coil X has 200 turns and the coil Y has 100 turns. When a current 4 amperes in coil X, which means I1 in coil X, and the change in flux in coil Y is 5 milliwebers. Okay, because due to the current flowing through the primary winding, there will be a change in flux in the secondary coil, that is coil Y, which is 5 milliwebers. Then determine the mutual inductance between the coils and the coefficient of coupling. Right. So first, let me draw the circuits for our better understanding. So here there are two circuits. One is X and are two coils that they have mentioned. So one is X and another one is Y. Right. So here the current flowing. Of course, this is the coil X that they are calling, and this is the coil Y that they are calling. Right, coil Y. And here N1 is equal to, which is 200, and here N2, which is equal to 100. And another one, here L1 is equal to 80 millihenries and L2 is equal to 60 millihenries. And another one, of course, when you current 4 amperes in coil X, so which means here, let us consider here I1, which means the change in current in the primary circuit. Okay, I1, which is equal to 4 amperes, let us consider, right? Then what we need to find the mutual inductance. So mutual inductance between these two coils and as well as the coefficient of coupling. Right. So first let me find the mutual inductance. Right. So usually the mutual inductance, there are two equations basically. Okay, because here we have already discussed where this one. Okay, so M is equal to N2 by I1. Right. M2 N2 by I1. So here M is equal to N2 by I1, right? So because here, of course, you may get doubt like, okay, why we should write this is N2 by I1 instead of that we can also write it as N1 by I2. Okay, but which equation we have to choose here? that is based on the what is that information that they have provided in the problem, right? So in the problem, what they trying to tell us is here, of course, the mutual induction is exists between these two windings. Okay, so here there is a change in current in the primary circuit. So due to that, the flux will produced by the primary circuit, and in that flux, some amount of the flux is linking with the secondary winding. Okay, so which means the change in flux. Okay, and what is the amount of the flux that is linking with the secondary winding also that they have given, which is 5 milliwebers. Okay, the 5 milliwebers is the flux. What is that? The flux linking with the secondary coil. Okay, which means, of course, here they mention that the change in the flux in the coil Y. So which means here, which is phi 2. So here it is phi 2 is equal to what is that? The 5 milliwebers. And that they are given when a current 4 amperes in the coil X. Okay. So why the change in flux is flowing in the coil Y? Because of the change in current in the coil A or coil X. So that change in current here also they provide that they have given, that is 4 amperes, right? So that's why here we should consider this equation. And of course we know the number of turns in the secondary coil also, which is 100 turns. So then substitute all these values here. Here N2 is 100 and phi 2 5 into 10 to the power of minus 3 by here I2 is 4 amperes that they have given. Then simplify this, then you will get here. Okay, so here which is 0.0625 henries, or in another words, let me see here, because I have already calculated this, which is 62.5 millihenries. This is the mutual inductance between the two coils. Okay, then if you know the mutual inductance, then it is very easy to find the coefficient of coupling. So because we know the direct equation for the coefficient of coupling, so K is equal to M by square root of L1 into L2. So M we know what is that value. Here it is 62.5 into 10 to the power of minus 3. 62.5 into 10 to the power of minus 3. Yeah, 62.5 into 10 to the power of minus 3 millihenries by square root of. So here the value of L1 is 80 and value of L2 is 60. So 80 into 10 to the power of minus 3 into 60 into 10 to the power of minus 3. Then if you simplify this, then you will get the value. Let me see here, it is 0.902. 0.902. Of course, there is no units for this particular, the value of the coefficient of coupling. So now here K is equal to 0.902. So here you no need to remember the equations. Okay, you just remember the concept or try to just understand the concept. Then automatically you can write the equations based on the concept that we are understood. Right? Okay. So that is very important point here. It is. So this is all about the coefficient of coupling. Okay, and some numerical problems based on this coefficient of coupling. Right. So in next class we will discuss about other topics from the magnetic circuits. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.